Hello and welcome to today's Explainer. I am absolutely thrilled to dive into this topic with you because today we are going to completely demystify Kubernetes. We aren't just going to throw technical jargon at you. Instead, we're going to start right at the root, looking at the massive problems that existed before Kubernetes, how brilliantly it solves them, and we'll break down its entire architecture in detail. By the end of this, you'll understand exactly how to orchestrate your containers like an absolute pro. Okay, let's dive right into this. Every developer out there has either said or heard this classic phrase, well, it works on my machine, right? You write this beautiful piece of code in Node.js or Python, you test it locally against your specific database version, and it runs flawlessly. But then you try to deploy it to a production server. You literally have to manually replicate that exact same environment, operating system, and dependencies. And the second you hit run, crash. It works on your machine, but nowhere else. So here's our roadmap for today. First, the code deployment problem. Second, the container orchestration solution. Third, the anatomy of the control plane. Fourth, worker nodes in action. Fifth, the Nginx scaling example. And finally, escaping vendor lock-in. Section 1. The code deployment problem. Let's set the stage. Back in the day, we relied on physical servers, literal bare metal machines sitting in an office or rented out. Scaling meant physically buying and installing new RAM or CPUs. It was incredibly expensive and slow. Then came the AWS and cloud-native era, making servers accessible with just a few clicks, but that trapped you into their specific tools. To fix that, it works on my machine issue, we got Docker and containers. Containers strip away that heavy operating system layer, creating a lightweight, perfectly shareable package of your code and its environment. It was a huge breakthrough, but it actually introduced a completely new nightmare. While containers are amazing, they come with massive challenges at scale. Picture this. Your app suddenly gets a huge spike in traffic. You need to instantly spin up hundreds of containers. Then, when traffic drops, you have to destroy them to save money. If a container crashes because of an error, it needs to be detected and restarted immediately. Is it even possible to do all of this manually? You'd need a team of developers just staring at screens 24/7. For any modern business, managing this lifecycle by hand is practically impossible. Section 2. The container orchestration solution. The magic key to solving this whole mess is container orchestration. This is simply the automated process of managing, scaling, deploying, and networking containerized applications. Basically, it means handing over all those tedious, practically impossible tasks we just talked about to an automated system. And nobody felt the pain of managing containers earlier or more intensely than Google. Google was already running millions of containers for search and Gmail using an internal tool called Borg. Realizing that eventually every business was going to need this kind of power, a team at Google took inspiration from Borg and built a brand new open source system. They called it Kubernetes. You'll actually see it abbreviated a lot as K8s, simply because there are exactly 8 letters between the K and the S. Fun fact, Kubernetes is a Greek word meaning helmsman or pilot, which makes total sense because it's literally steering your ship of containers. In 2014, Google donated it to the Cloud Native Computing Foundation, making it free and accessible for everyone. Section 3, Anatomy of the Control Plane. Now, what's really interesting about this slide is seeing how these 4 components work together on a physical machine to act as the brains of your entire system. First up is the API server. This is your gateway. It's the only part you, the developer, actually talk to when giving instructions. Then there's the controller. Think of it as the manager that takes those instructions and makes all the operational decisions. Next is etcd, which is a highly available key-value database. It acts as the memory of the system, storing the state of literally everything happening inside. Finally, the scheduler watches for new workloads and distributes them to the best available machines.
Section 4. Worker nodes in action.
So the control plane handles the management, but where does your actual application live? That's where worker nodes come in. This is the brawn of Kubernetes. These are the separate physical or virtual machines where the actual heavy lifting happens. Each node has 3 critical pieces. The kubelet is the agent that constantly talks to the API server, receiving orders and reporting back its status. The kube proxy handles all the networking and traffic roles, making sure user requests actually reach your app. And the container runtime interface, or CRI, like Docker or Containered, is the actual engine that runs the containers at the physical level. But here is a really crucial detail you need to know. Kubernetes doesn't actually run bare containers directly. It wraps them in something called a pod. A pod is the smallest deployable unit in Kubernetes. You can kind of think of a pod as the soul of your application. It holds your container and its configuration, just waiting to be assigned to a physical worker node so it can come to life.
Section 5. The Nginx scaling example.
Let's move to and see how this builds in a real-world step-by-step example. Imagine a massive traffic spike hits. Step 1. The developer tells the API server, hey, I need 5 Nginx containers right now. Step 2. The API server authenticates this and tells the controller, which instantly creates 5 new Nginx pods. But right now, they're just floating in the system. They don't have a home. Step 3. The scheduler spots these unassigned pods and distributes them across your available worker nodes to balance the load. Step 4. The kubelet on those specific worker nodes receives the command and tells the CRI to physically start those containers. And boom! Your system has successfully scaled up. Okay, so the traffic spike is over. Now you tell the API server you only want 1 pod running so you can save some money. This brings us to the absolute core philosophy of Kubernetes: desired state versus current state. Kubernetes is a system that is constantly, obsessively, trying to match the system's current reality to the desired reality requested by the user. So what actually happens behind the scenes during this scale down? Step 1. The API server checks the etcd database, which, remember, holds the ultimate truth of the system. Step 2. It realizes the current state is 5, but the new desired state is only 1. Step 3. It immediately sends a command to the kubelets on the worker nodes. Step 4. The kubelets gracefully terminate 4 of those containers. Now, the current state perfectly matches the desired state, and this automated reconciliation loop runs continuously. Even if a container crashes entirely on its own, the system will instantly recognize the mismatch and spin up a new one automatically to reach that desired state.
Section 6. Escaping vendor lock-in.
Think back to the cloud era we discussed earlier. If you use a service like AWS Elastic Container Service, you're writing your deployment pipeline specifically for AWS. You become completely reliant on their proprietary load balancers and tools. This setup is a massive trap. Why? Because if AWS jacks up their prices tomorrow and you want to move to DigitalOcean or Google Cloud Platform, you are looking at a huge engineering headache. You'd essentially have to rewrite your entire deployment pipeline from scratch because those AWS-specific commands just won't work anywhere else. And this brilliantly illustrates our final major benefit. Kubernetes solves this trap perfectly using the Cloud Control Manager, or CCM. You see, Kubernetes is entirely cloud agnostic. When you need a load balancer, which is a piece of cloud-specific networking hardware, Kubernetes doesn't build it itself. Instead, you give the instruction to Kubernetes, and the CCM automatically talks to the specific API of whatever cloud you happen to be running on. It translates your generic Kubernetes command into an AWS command or a GCP command on the fly. This means you only ever write your configuration for Kubernetes once. You could literally lift your entire infrastructure and move it to any cloud provider in the world without rewriting a single line of code. Which brings us to our final question for you to ponder. If a massive traffic spike hit your application right this very second, would your current infrastructure automatically scale to meet the demand, or would it simply crash? Understanding Kubernetes isn't just about learning a new tech tool. It's about escaping fragile manual chaos and stepping into the power of resilient automated orchestration. Thank you so much for joining me in today's Explainer, and I really hope this gives you the confidence to start exploring Kubernetes in your own projects.